Welcome to another topic in Richard James Mathematics Resources. This is topic number 31, and it is distance time and velocity time graphs. Not all topics in mathematics are based on fundamental principles of their own. This topic is one of many that makes use of the principles that are presented in other topics. This and other such topics constitute applied mathematics. Sometimes an entire subject may be applied mathematics. One such subject is principles of accounts. Some subjects require knowledge of advanced mathematics. While attending the university, I was informed that most of the senior lecturers in the Department of Economics completed mathematics majors in their first degree. I was told that in order that I may have an idea how mathematical economics can be at the bachelor's degree level. I am a musician, and surely music theory is applied mathematics. The principles of playing string instruments are also very mathematical. Mathematics has its role in almost every other subject area. What about language? While at the university, I studied in the Department of Language and Linguistics. I successfully completed a course in which mathematics, specifically set theory, was used to determine the validity and hence soundness of an argument. Let us therefore not be afraid to apply mathematics, but use it to our advantage in all aspects of life. Since this topic is an applied mathematics topic, it must adopt principles from other topics. It should not be surprising that we are using principles from functions and graph. After all, this is another topic in functions. The first to be considered is finding the gradient of a line that is given by the change in y divided by the change in x. So let us look at that. And that is taken without any alteration from the topic equation of a straight line. We are saying that y2 minus y1 over x2 minus x1 is equal to gradient. And that is equal to y1 minus y2 over x1 minus x2. Of course, we know that the coordinates of 2 points that are involved will be x1, y1 and x2, y2. The statement of this formula tells us that irrespective of the point that we use first, the gradient is always going to be the same. We need to be able to find the area of an irregular shape, and our worst case scenario is finding the area of a trapezium. A is equal to b over 2, and in bracket we have h1 plus h2. h1 and h2 are the two parallel sides, and b is the perpendicular distance between the two parallel sides. As a matter of fact, when we are solving the problems in this section, a better understanding of the application of these formulae that are adopted from other topics will be understood. Of course, h1 and h2 are the two parallel sides, and b is the perpendicular distance between the two parallel sides. We may also be required to find the gradient of a curve, as in volume 2. Volume 2 is functions part 1. By drawing a tangent to the curve and find the gradient of the tangent by using the formula above. Gradient of a tangent may be found by using this same formula that is applicable to gradients in general. The next two slides contain some points that we may use when drawing conclusions and making calculations involving velocity time and distance time graphs. Here we have a lot of information on the slide. The gradient of the curve of a velocity time graph, because we are looking at the specifics of velocity time graphs. The gradient of the curve is used to determine the acceleration. The area under the curve in a particular region is the distance traveled in that region. A horizontal line represents a region in which velocity is constant and the acceleration is equal to 0. A point on the horizontal axis tells us that the particle is not moving, velocity is equal to 0, the particle is at rest. Average speed is equal to total distance divided by total time. At a point on the vertical axis, time is equal to 0 and the value of the velocity indicated is called the initial velocity. A line that slopes upwards, which is a positive slope, tells us that the particle is accelerating. A line that slopes downward, which is a negative slope, tells us that the particle is decelerating. In any event that a reference should be made to these points, the accompanying booklet should be used. However, in each particular section, the principles that is to be used are applicable to a particular problem will be discussed in detail. Distance time graphs. The gradient of the curve tells the speed of the particle. A horizontal one represents a region in which distance moved is a constant. That means the distance is not increasing, the distance is not decreasing. That means the particle is at rest. A point on the horizontal axis tells us that the particle is at the point of reference and distance from the point of reference is equal to 0. The average speed is equal to the total distance divided by the total time. At a point on the vertical axis, the particle is at some distance from the point of reference, but the process has not yet started. This means that the process did not begin with the particle at the point of reference. A straight line that is inclined to the horizontal tells us that the particle has a constant speed. The figure represents the distance time graph. Of course, we are not looking at the figure now, we are looking at the statement of the problem. The figure represents the distance time graph of two persons, Andy and Bob, journeying between two offices, M and N. Andy leaves M at the same time that Bob leaves N. Use your graph to 1. Determine the distance Mn. 2. Determine how much time Andy spent in walking between M and N. 3. Determine how far from M Andy and Bob met. Calculate Andy's average speed for the whole distance. Explain fully the segment PQ on Bob's graph. The distance Mn may be determined in two ways. The first is by counting the number of units between M and N. So let us do that. The beginning position at M is 0 unit. We haven't started as yet. We count the units until we reach M. 2, 3, 4. 1, 2, 3, 4. 4 units. So Mn is equal to 4 kilometers. We may also find the distance Mn by calculating the difference in distance between the 2 points. So take note of the location of the points M and N and the distance associated with them. So we have point M and we have point N. What is the distance associated with them? The points are located at 0 kilometer and 4 kilometers. So Mn is equal to 4 minus 0. So Mn is equal to 4 kilometers. We may take similar approaches in finding the time that Andy spent in walking from M to N. M is at our typical origin. Let us only worry about finding the time on Andy's graph associated with N. Draw a dotted line horizontally from N to meet Andy's graph. So let us do that. There it is. And let us draw another one that goes from the graph to the time axis. So we're going to go from the graph to the time axis, which is right here. That is the line, and it is at 40. So let us count the number of units from M to the dotted line along the time axis, beginning at 0. 10, 20, 30, 40. So time is equal to 40 minutes. We may also find the difference in time between the 2 points. That's another way. So right there we have 0 minute, and here we have 40 minutes. So time is equal to 40 minus 0, and that is 40 minutes. So irrespective of the approaches are very simple. The answer is 40 minutes. To find how far from M Andy and Bob met, let us first identify the points where they met. So let us identify where the graphs cross each other. They meet at the point of intersection of the two graphs. On the distance axis, we will insert pointers in order to identify the distances associated with M and the point where they meet. So we are trying to find how far from M they meet. So put a pointer at M and another pointer at the level on the distance axis where they met. Take note of the location of the points M and N and the distances associated with them. The pointers are located at 0 kilometer and 2.2 kilometers. The distance is equal to the difference between the two values. So we have 2.2 kilometers. Whenever one of the points is located at position 0, we do not need to go through a process to find the difference. Finding the location of the other point will give us the answer, since subtracting 0 does not affect the number from which we are subtracting it. Average speed is equal to total distance divided by total time. To find Andy's average speed, we need to divide the distance traveled by the time taken. That is our distance traveled, and that is our time taken. So the speed is equal to distance divided by time. So the speed is equal to 4 kilometers divided by 40 minutes. One reason why it might not be appropriate to cause the time in minutes to remain in the calculation is that kilometer per minute is not a typical unit of speed. Another is that numerical value of the speed might be more acceptable if a popular unit is used. Finally, calculating the speed using minutes may cause the implied intention of the examiner to look ridiculous. So let us change the time in minutes to hour. Divide the time in minutes by 60, converting it to hour. When dividing by a fraction, we invert and multiply. So we are going to invert that. Instead of 40 over 60, now we have 60 over 40. So we have inverted and we are multiplying. Turns out that the speed is equal to 6 kilometers per hour. Let us give every detail about the segment PQ on Bob's graph. First, let us insert pointers and dotted lines that may be used in our analysis. So we are going to describe fully the segment PQ on Bob's graph. And we are inserting pointers at every important point. The distance that Bob walked from his beginning point at N to the point P may be found by considering the two blue arrows. We are going to be looking at the distance that Bob traveled in moving from N to where PQ may be found. So we are looking at this distance. So D is equal to 4 minus 2.5. The upper or the larger value is 4 kilometers and the smaller one is 2.5 kilometers. So 4 minus 2.5 is 1.5 kilometers. That is the distance that Bob walked. The time that he takes to get there is dependent on the second red arrow, since the first one is at t is equal to 0. So what about the time that he took to get there? Right at this second arrow, which is 15 minutes. Right at this arrow. So the time is 15 minutes. PQ is horizontal, demonstrating a period of time for which Bob rested. The blue dotted lines accompanied by two arrows are indicating this. So here we have them. The region in which Bob is at rest. And of course this is 20 and this is 15. So the period of time is 5 minutes. So we are going to describe this section fully by saying, after walking a distance of 1.5 meters that takes 15 minutes, Bob rested for 5 minutes. We have another problem. The distance s in meters moved by a particle from its starting point at time t seconds is given by s is equal to 3t plus t squared. We are required to copy and complete the table below, this table here, using a scale of 1 centimeter to represent 1 second and 1 centimeter to represent 10 meters. Draw the graph of the function for the range, like what we have had before. 0 is less than or equal to t is less than or equal to 8, or t will range from 0 to 8 inclusive. Using the graph, estimate the distance moved in 4.5 seconds. Draw the tangent to the curve at t is equal to 6. Estimate the value of the tangent at this point and give an interpretation of this value. So our first duty is to complete that table. We will complete the table by finding the missing value of s for the associated values of t. This is done by substituting the relevant values of t into the equation. And let us see our equation is that. And of course, the first one that we need to find an associated value for is t is equal to 0. So where we see t, we put 0. So we are going to have 3 times 0 plus 0 squared. And of course, simplifying 0, 0, and that is equal to 0. And that is inserted right there in its rightful place. When t is equal to 1, 3 times 1 plus 1 squared, and 3 times 1 is 3. 1 squared is 1. So we are going to have 3 plus 1 is equal to 4, and that will take its place right there. And we are going to move on to t is equal to 4. So 3 times 4 plus 4 squared. 3 4 is 12. 4 times 4 is 16. So 12 plus 16, and that is equal to 28. Finally, s is equal to 8. So 3 times 8 plus 8 squared. 3 8s 24, and 8 8 64. The result gives 88, and that value goes there. Now that we have completed the table, we will proceed to plot the points. 0 0. Of course, the first point has no t and no s movement. It is therefore placed at the origin. 1 4. Next in line is t is equal to 1 and s is equal to 4. 1 for t, 4 for s. And the point is placed right there. Now plot the point t is equal to 2 and s is equal to 10 as indicated right there. 2 for t and 10 for s. The point goes right there. Let us plot the other points, and we are going to do the same thing. So we have 3 18, so 3 for the t and 18 for the s. We have 4 for the t and 28 for the s. Next we have 540. So 5 for t and s is 40. Another point is 654. 654. The point is placed right there. And 770. 770. And finally, we have 880. The curve may now be drawn. That's our curve. As neat as you can get. To estimate the distance traveled in 4.5 seconds, first draw a vertical line at 4.5 to meet the curve. So go to 4.5, draw a vertical line, right like that, meet the curve there. Then what are we going to do to find the distance? Go across there. So at the point of intersection of the line and the curve, draw a horizontal line to meet the other axis. It crosses the axis at 3.4 meters. The distance traveled in 4.5 seconds is therefore approximately 34 meters. To draw the tangent to the curve at the point where t is equal to 6, first locate the point on the curve by drawing a vertical line at t is equal to 6, and that vertical line will meet the curve at the point where t is equal to 6. And we are going to be applying knowledge that we have acquired from other subtopics, like the gradient of a curve. So now draw the tangent at the point where the line meets the curve. That's it. To find a value for the gradient of the tangent, find two convenient points through which the tangent passes. Some students, when they encounter a problem like this, after drawing the tangent, they find two convenient points that are on the curve. Well, what would be the use of drawing the tangent if the points that you are going to use are on the curve instead of on the tangent? The two convenient points must be points on the tangent. You are going to use those 2 points to find the gradient of the tangent, and we are going to be using the formula to determine the gradient of the tangent. And that formula is taken without any changes made to it from equation of a straight line. y2 minus y1 over x2 minus x1. Difference in y, difference in x. So we are going to put the values of x and y in their respective places. So we have, for the y's, we have 8.5 minus this other y value, 8.5 minus 15, and for the x's, we have 8 minus 3.5. That gives 70 divided by 4.5, and our gradient is 15.6. The gradient of a distance time graph, do not forget, or if you could not remember, go straight to the section in the booklet that outlines them. The gradient of a distance time graph gives the value of the speed. We may therefore interpret the result as the speed reached by the particle after it has been moving for 6 seconds. This is another problem. The velocity time graph represents the journey of a cyclist between 2 points, and of course, the graph is not on this page. Using the graph, determine by stating the units used, the length of time during which the cyclist accelerated, the acceleration, the length of time during which the velocity was constant, the deceleration, the total distance traveled, the average speed for the entire journey. So, the region in which the cyclist accelerated is shown by an increase in velocity and is marked with the blue line. That's your blue line that marks the region in which the cyclist accelerated. What is the time associated with that region? 2 pointers mark the interval of time involved from here to there, and we can see that t is equal to 3 minus 0, which is equal to 3 seconds. The gradient of a velocity time graph gives the acceleration. In order to find the acceleration, we therefore need to find the gradient of that line that slopes right here. In finding the gradient, we may divide the vertical movement of a line by the horizontal movement. 2 red pointers will mark out the vertical interval. So that is 80 minus 0, which is 80 meters per second. The gradient is equal to the difference in the velocity divided by the difference in time. Acceleration is equal to 80 divided by 3. Acceleration is equal to 26.67 meters per second square. We may take another approach to finding the gradient and hence acceleration of the cyclist. Let us identify 2 convenient points through which the line passes. So we have 2 convenient points through which the line passes. One, we have chosen the origin 0, 0, and the other one has coordinates 3, 80. One of the points is the origin. It is always a very convenient point to use if the line passes through it. The formula that is used in the topic equation of a straight line may be used to find the gradient of the line, hence the acceleration. So we are going to do y2 minus y1, 80 minus 0 over 3 minus 0. Substitute the ordinates of the points in their respective places in the formula, and that is what we are going to do immediately. So the acceleration is 80 divided by 3, and that is the same as we had before, 26.67 meters per second square. A region of constant velocity is depicted by a horizontal line. And there's your horizontal line. The 2 pointers mark the interval of time involved. So we begin at 3 seconds and we end at 8 seconds. Therefore, the time involved is 8 minus 3, which is equal to 5 seconds. The gradient of a velocity time graph gives the acceleration and also deceleration. So we are going to find the deceleration in this case that is related to this line. The region of deceleration is depicted by a line of negative gradient, and we use in our initial topic a little rule of thumb to identify lines that are of positive or negative gradient. The one with the uplifted left hand, or slopes in the direction of the uplifted left hand, is our line of negative slope, and this one is representing a deceleration. So the velocity is decreasing, and that is indicated by a negative gradient or by the uplifted left hand. The gradient may be found by dividing the vertical shift, which is 80 minus 0, and that is going to be 80, by the horizontal shift, which is 10 minus 8, and that is equal to 2. But don't forget that we have a negative slope, so the deceleration is equal to negative 80 divided by 2, and that gives negative 40 meters per second squared. A deceleration is a negative acceleration. This is not a surprise if we consider that the graph has a negative gradient in the region where deceleration is taking place. We may take another approach in finding the deceleration. This time we will identify 2 convenient points through which the line depicting the deceleration passes. So we have 880 right there, 880, and here we have 10 for the x, no y movement or no movement in the direction of the velocity axis, so 0 for the accompanying velocity ordinate. The formula that is used in the topic equation of a straight line may be used to find the gradient of the line and hence the deceleration. So that is your formula. Of course, we are going to use 80 minus 0 over 8 minus 10. Substituting the ordinates of the points in their respective places, and if we do that, this is going to be the result. And 80 minus 0 is 80, 8 minus 10 is negative 2, so we have 80 to be divided by negative 2, and the result is negative 40 meters per second squared. When a pure mathematical principle is applied to a real-world situation, the result can turn out to be quite truthful. The value of the result being negative correctly demonstrates that the speed is decreasing. That is correct. When using a velocity time graph to find the distance traveled, we need to find the area under the curve in the specified region. On this occasion, the total distance is required, so we need to find the area under the curve throughout the entire journey. The area is in the shape of a trapezium whose area is given by, remember the area of a trapezium? What is given by? B over 2 H1 plus H2, in which, of course, here we have our trapezium, that is the shape of the area that is under the curve for the entire journey. And of course, H1 and H2 are the two parallel sides. Those are the two sides that are parallel to each other, H1 and H2. And of course, B is the perpendicular distance between the two parallel sides. We are familiar with the dimensions of the figure. B is the total vertical height of the graph, right there, which is 80 meters per second. H is the region in which the velocity was constant, from here to here. And that we know to be 5 seconds. H2 is the entire distance here, or the entire interval here, and that is equal to 10 seconds. D is equal to 80 over 2, because we are saying B over 2. B is 80, as we can read from the axis, and that we have done before. 80 over 2, and the two parallel sides, one is 5 and the other is 10. So that is what we have right there, and by simplification, 40 times 15, which is equal to 600 meters. The average speed is found by dividing the total distance by the total time. The total time is equal to the time for the entire journey, and that is 10 seconds. So the speed average, or the average speed, is equal to 600 divided by 10, and that is 60 meters per second. Now we have another problem, in which this time we are going to be required to draw a velocity time graph. A car starts from rest and accelerates for 5 seconds to a point P, reaching a velocity of 30 meters per second. It maintains this velocity for 10 seconds. Using 1 centimeter to represent 2 seconds on the time axis, and 1 centimeter to represent 5 meters per second on the velocity axis, draw the velocity time graph for this part of the car's journey. Using your graph, calculate the velocity of the car after 2 seconds, the car's acceleration in the first 5 seconds, the distance traveled in the 15 seconds, and of course the average speed for the 15 seconds. So, a car starts from rest and accelerates for 5 seconds to a point P, reaching a velocity of 30 meters per second. So let us see how we put that on the graph. So let us first indicate 5 seconds. Where's 5 seconds? Right there at the tip of that arrow. 5 seconds. And of course, next indicate the 30 meters per second, because it reached a velocity of 30 meters per second. So let us go for the 30 meters per second right there. Now insert the line that indicates that part of the journey. It maintains this velocity for 10 seconds. A region of constant velocity is represented by straight horizontal line. So the constant velocity was maintained for 10 seconds. The first part of the journey is 5 seconds. An additional 10 seconds will take us from 5 seconds to 15 seconds. That is the line that indicates the constant velocity of 30 meters per second for 10 seconds. To find the velocity after 2 seconds, first draw a vertical line at the 2 seconds mark to meet the curve. Right there. At the intersection of the line and the curve, draw a horizontal line meeting the other axis. So we have 2 seconds up there, then we go across, and that's all there is to it. Now, it crosses the axis at 12.5 meters per second. This is the speed after 2 seconds. So the speed after 2 seconds is 12.5 meters per second. The acceleration from a velocity time graph is the gradient of the curve in the specified region. This can be found by dividing the vertical movement in the region by the horizontal movement. Again, pointers will be used to indicate the vertical and horizontal positions where the given instant of time begins and ends. The vertical portion begins at 0 and ends at 30. The length of the interval is therefore 30 meters per second. The horizontal portion begins at 0 and ends at 5. This accounts for 5 seconds. So the acceleration is 30 divided by 5, and that is equal to 6 meters per second squared. To find the distance traveled, we need to find the area under the curve. So take note of the word under. Some students believe that for this problem, finding the area is impossible because the curve is not closed. We are not to find the area that is enclosed by the curve, but the area that is under the curve. And this can be done by finding the area under this graph that we have right there. Again, the area under the curve is in the shape of a trapezium. Right, and the area of the trapezium is given again. The formula for that area is given again. And of course, H1 and H2 are the two parallel sides, and we identify them. And of course, the perpendicular distance between the two parallel sides is the value of B. Good. B is equal to 30 meters per second. H1 is the region in which the velocity was constant, right here, and that is 10 seconds. And H2 goes from 0 to 15 seconds, and that H2, the value of H2 is 15 seconds. So, substituting into the formula, we have 30 divided by 2, 15 plus 10, and when we simplify that, we get 15 multiplied by 25, and that gives us a distance of 375 meters. The average speed is found by dividing the total distance by the total time. The total time is equal to the time for the entire journey of 15 seconds. So speed, average or average speed, is equal to 375 divided by 15, and that gives 25 meters per second. And finally, we have a problem with a very short statement, but it deserves some serious consideration because of its algebraic nature. The velocity time graph shows the movement of a particle along a straight line. The particle passes a point A when t is equal to 0. it maintains a constant speed u meters per second for t seconds and then decelerates uniformly before coming to rest at b. If the average speed for the whole movement is 40 meters per second, calculate the value of u. Given that the deceleration between t seconds and 4 seconds is 5 meters per second squared, calculate the value of t. 2 parts, but let's see what we make of it. That is our graph. The average speed for the whole movement is 40 meters per second, and we are required to find the value of u. Now, what is average speed equal to? We first need to find the distance traveled by calculating the area under the curve, because average speed is equal to total distance over total time. So we need to find the distance traveled by calculating the area under the curve, and of course this time it is also in the shape of a trapezium. And of course, let us identify the parallel sides h1 and h2 as before. Right. B is the perpendicular distance between the parallel sides. That is our B. B from here to here is given as u meters per second. Therefore, the value of B is u meters per second. H1 is a region in which the velocity was constant and is t seconds. This region here, see right there, and that the time associated is from here to here, and that is t seconds. H2 goes from 0 second to 4t seconds. That is from here all the way down to there, and so it is equal to 4t seconds. So the distance is equal to u over 2 to be multiplied by t plus 4t. And let us simplify that. U over 2 and t plus 4t is equal to 5t. So we have 5ut divided by 2. So the average speed is 40 meters per second. This is equal to the total distance divided by the total time. The total time is 4t. So we know the average speed to be 40 meters per second. So then 40 meters per second is equal to the total distance that we have from here to be divided by the total time, 4t. Let us continue to simplify the expression. So what do we have? We have 5ut over 2 multiplied by 1 over 4t. And that turns out to give 5ut multiplied by 1 is 5ut, and 2 times 4t is 8t. Of course, the t's will cancel each other, and we'll proceed by transposition of formula. And when we transpose, what do we get? We are trying to find u. We are dividing by 8, so we multiply by 8 on the other side. Of course, u is being multiplied by 5 here, so we divide by 5 on the other side. So u is equal to 40 times 8 divided by 5, and that is equal to 64 meters per second. Now, given that the deceleration is 5 meters per second squared, find the value of t. What is deceleration? Of course, gradient. Let us identify 2 convenient points through which the line depicting the deceleration passes. And we are finding 2 convenient points because we need to find the gradient. The deceleration is going to be found by calculating the gradient. So we have 2 points, one right here where t is equal to 1 and the velocity is u, and here where the time is equal to 4t and the velocity is 0. So we have t, u, and 4t, 0. And of course, we know the value of u from the previous example to be 64 meters per second. Of course, let us find the gradient as usual. So we have 0 minus u over 4t minus t. And we have, this is equal to the deceleration, that is equal to 5 meters per second squared. So this gradient will turn out to be what? The deceleration, 5 meters per second squared, and the value of u is 64. So we have the gradient, the deceleration, -5, and when we simplify this, which is a representation of the gradient, we have 0 minus u is negative u, 4t minus t is equal to 3t, right? And of course, we are going to make use of the fact that u is equal to 64, and we are going to transpose that expression in order to find the value of t. So this t is going to be multiplied here, and we are going to be dividing by 5 on the other side. Of course, after doing that, we'll have a negative numerator and a negative denominator, and the entire expression will turn out to be positive. Of course, I'm not going to be going through any great detail in transposition right here, or solution of linear equations, because we have allotted an entire volume to all of the basic work in algebra, and that is volume 1. So t is equal to 4.3 seconds